Hello Science Alliance, hello my IGCSEs. It's the second electricity lesson. You don't really need to have seen the first electricity lesson. If you're watching live, you knew. Just do it, just jump in. What have you got to lose? Can you please, I'll do a recap of last lesson while we're just getting ready for this activity. If you've got some sort of clean, thin plastic packaging from the recycling on you, or like a 5p plastic bag, can you just cut a tiny little bit off it? Not too much. I don't want you to like ruin a plastic bag. No way. You've got to be able to reuse those. But if you could just cut like maybe a tiny little bit off the handle or something like that. I just want you to have a small piece of very thin plastic. And what we need to do is we need to charge it up. And we learned last week that how you do that is you rub it on your head. Or if you haven't got any hair, then you could rub it on a kind of any kind of fluffy, staticky jumper or pair of socks. That would work as well. All right, so get rubbing it on your head, please. Cut out a tiny little bit of sort of plastic, bit thicker than cling film, and then start rubbing it on your head. And while we're doing that, I will briefly, I can feel it's really staticky, briefly remind us all what we did last week. So last week we were looking at atoms. I mean, a lot of you will know this already. Inside an atom are tiny little positive particles called protons. I can't, it's like that, I can't rub and do drawing at the same time. Oh, hello, I've got the comments on. Oh, that's fun. Oh, I didn't know I'd done that, but brilliant. Hello, feel free to comment. And then whizzing around the protons in a sort of cloud are these teeny tiny little negatively charged particles called electrons. So last week we looked at how when you rub a plastic bag on your head, what is actually happening. And it seems incredible, but what is happening is you are pulling electrons off the plastic bag and the electrons are going onto your head. So I was saying how most of the time atoms have got the same amount of protons as electrons. I better label those, hadn't I? Electrons, just in case anyone's very new to this. So the protons and the electrons, you have the same amount of both and they cancel each other out. So atoms usually have no charge at all. They've got a neutral charge. But when you rub a plastic bag on your head or on a jumper, it pulls electrons off the plastic bag and onto your hair. People were asking me how you know which direction the electrons go in. You will never have to do that for an exam, or they will tell you. Like sometimes if you pull a jumper on over your hair, sometimes electrons move like from your hair to the wool or something. It doesn't really matter which way around. But anyway, what ends up happening is the place the electrons are going to ends up being slightly more negative because it's got extra electrons. And the place where the electrons have come from ends up slightly more positive because it's lost some electrons. And last week we were looking at how positive and negative things are attracted to each other. A better way of saying that in physics is like charges attract. Sorry, I always get this wrong when I go for the proper language. Unlike charges attract. So a positive and a negative, they are unlike each other. And unlike charges attract. Like charges, like two positives or two negatives, repel. Unlike charges attract. Like charges repel. Not that hard. So anyway, yeah. So if you've rubbed a little bit of plastic on your head now, what you will hopefully find is, again, if you haven't got hair, you could just put it really near the jumper that you rubbed it on. You will find that you can kind of make the hair and the plastic be attracted to each other. Yeah. So if I put that little bit of plastic on my head now, it sticks because the plastic is more negative, the plastic is more positive, and the hair is more negative. And unlike charges attract. So what's going to happen if I stick this little bit of plastic to my whiteboard? If you are in a room with walls, do this with me. Try sticking the bit of plastic to the wall. What happens? Gasp! It sticks. What's going on? Because the wall isn't charged. We didn't rub the plastic on the wall. Why is it sticking? And I've said, can you think of anywhere where this little bit of plastic will not stick? Can you think of anything the plastic will not stick to? It was such a great question, I wrote it down. Can you think of anything that this little bit of plastic won't stick to? Think of any materials? Any materials that it won't stick to? You think of anything? I have actually got comments on this, so I could ask you. But in previous Facebook lessons, where the comments are a bit more visible to me, have said things like, try the wooden shelves behind you. Okay, I'll do that. Imaginary people, you haven't asked me. Oh, it sticks! Something of a like. Oh, Jacob's saying something of a like charge. Oh my goodness, that's brilliant. Wait, so we're saying that the plastic bag has a negative charge. That is actually brilliant. I haven't done that before. Holy smokes, I'm going to do it right now. I've actually got another bit of plastic here. So a common answer is, I said to bring an aluminium can with you if you want to do the activity this week. Will it stick to the aluminium can? Do you think it will, or do you think it won't? It does. It does. But I've never had anyone say, try it on an object that has the same charge. So you might want to do this with me, actually. I'm going to do Jacob's idea right now. Hooray for YouTube comments. I'm going to get another piece of plastic and rub it on my hair, because then whether it's positive or negative, it doesn't matter with it, does it? They'll both have the same charge because they've been treated the same way. And see if they stick to each other. While I'm doing that, oh no, let's just do it now. It won't take long, will it? I have got a question sheet for you, but okay. If this was a fair test, I would obviously have had to have rubbed the bits of plastic for the same amount of time. Can't do that, can I? Because one of the bits of plastic has already been rubbed, but it should be okay. I'm wondering how to do it, because I don't want... I tell you what, I'll just hold them by the edges and then move them towards each other. That's the best way of doing it. Because if I just hold them, they might just stick to my hand instead. Okay. Well, they are stuck to my hands. Okay, holding them. Not very scientific. If I move them towards each other. Oh, they are actually pushing away from each other. Oh my goodness. Jacob, you're a blooming genius. Yeah, it's not sticking anyway. Oh, that's amazing. It's sticking to my hands. Oh yeah, someone said flesh on Facebook yesterday. Yeah, it will stick to my flesh, but it absolutely will not stick to the other bit of plastic. Oh, brilliant. Right. Do this sheet for me. Can you tell me, please, are any of these statements not true? Oh no, Jacob, you're the one whose bit of plastic isn't sticking to anything. What? Maybe you're using the wrong bit of plastic. This bit that I was using to demonstrate with the electrons on it isn't actually very staticky. It's not you, dude, it's the plastic. Right. Are any of these statements not true? Electrons can be transferred between objects. Is that true? Materials can be tested to find out if they're charged. Is that true? Charged objects aren't attracted to neutral objects. True. Electrons can move from balloons to hair. Opposite charges attract. Electrons can flow through humans. Atoms have positive charges at their centres. Are any of those statements not true? I'm getting a bit of a sore throat, so I'm trying to do proper good centred actor voice. Behold the statements. But is there truth to them, forsooth? Decide immediately. I'm just going to drink some of the milk, some of the almond milk that I used in the blobfish lesson, because I've got a sore throat. Delicious. Okay. Are you ready? Some people on Facebook yesterday were saying, oh, I bet it's, no, none of them are not true. All of them are true. That is the kind of thing that I would do. Yours isn't. You used a thin plastic carry bag and it's not sticking. Is your hair wet? Has your hair maybe got product in it? If you've used conditioner, then it's harder to get your hair to be staticky. Maybe used a woolly jumper instead or something like that. I must be a very staticky person. Anyway, electrons can be transferred between objects. Yes, like hopefully we've just done that. You've just charged up a plastic bag, so the electrons have definitely moved between the bag and the hair. Electrons can move from balloons to hair. I mean, you might not have known that was true, but yeah, it's pretty much true. Opposite charges attract, definitely true. What's the proper physics way of saying that? Go on, say it out loud. How do you say opposite charges attract in a proper good physics way? Unlike charges attract. Unlike charges attract, true. Electrons can definitely flow through humans. Yes, they can. That's what electricity is. Electricity is charged particles moving, and electrons flowing through humans would be a human probably getting a bit of an electric shock. Atoms have positive charges at their centres. Yes, they're called protons. We've looked at that. Charges aren't attracted to neutral objects. Well, that's not true, is it? Because I just did it. I just stuck a charged bit of plastic to a wooden shelf which wasn't charged. So that is false. But materials can be tested to find out if they're charged. We did that last week. Right. So what is going on? How do things that aren't charged get attracted to things that are charged? Well, one of the ways we looked at last week we looked at how you can make water move using a charged object. Water can be like attracted to a charged object, and that's because water particles have this thing that we call a dipole, which means one end of the water particle is slightly positive and one end of the water particle is slightly negative. I don't think you need to know that for your IGCSE, but it's interesting. So overall, water particles are still neutral, right? They've got the same amount of positivity and negativity, it's just that they're in slightly different places. So that's how the water trick that we did last week worked. But that is not how this next thing that we're going to do works. Oh yeah, we looked at how paper sticks to a charged bit of plastic, didn't we? We looked at how when you rub a bit of plastic on your head, it can pick up tiny little bits of paper. How is this? That's kind of like the same as this little bit of plastic sticking to a bit of wood. How does that work? I'm going to let you think about it for 10 seconds using this diagram to help feed your brain. So this is a wall here. It could be a wooden shelf or a whiteboard. Let's just say that this is the wall and these are the atoms in the wall. So they've got the same amount of protons and electrons whizzing around them. So the wall is neutral. Obviously the electrons are free to whiz around the protons. How does a bit of plastic, charged plastic, stick to a neutral wall? I am just going to let you think about it for 10 seconds and then I'll put another picture on the board which might help you think. Okay, here's your extra food for your thoughts. There's a picture of a balloon which is negatively charged. So that's basically what we just did, isn't it? I mean, our bit of plastic is probably positively charged, but it really doesn't matter. It's the same effect both ways. Let's have a look using the PowerPoint special effects. So let's say we've got a negatively charged balloon. The negatively charged balloon approaches the wall. We've got negatively charged electrons that are free to move around their protons. So what do? Well, those are like charges. So they're going to repel each other. So the electrons basically just try and get as far away from the negatively charged balloon as they can. So what's happened? Well, one side of the wall, facing away from the balloon, has now got a lot of negativity sort of bunched up on it. And the other side of the wall is overall more positive. So the balloon and the wall are attracted to each other. So a tricksy question for you. We did this activity kind of the same thing last week. A charged balloon picked up little neutral bits of paper. It's very similar to the wall that I just showed you. Is the paper charged in this scenario? When a negatively charged balloon picks up little bits of paper, is the paper charged in that scenario? Can you explain why or why not? You can say it out loud, you can scribble it down. If you've got the worksheet from my website, you don't need it to do this lesson, but if you have, then you've got this written in front of you. I know this is a good question because people on Facebook were giving me all different answers, which is always a good sign that I'm making your brains work. The answer is no. The paper is not charged in that situation. The paper still, just like the wall, it's still got the same amount of positive and negative charge. It's still neutral. It's just that the charges have moved around. So in this case, the electrons, again, they would have been repelled by the balloon. So on one side of the paper, that it would be slightly more negative. On the other side, it would be slightly more positive. And then the positive side gets attracted to the balloon. But the paper itself is still, it still has a neutral charge. Right, because it's exactly the same situation as this. It's just the charge moving around. Okay, have you brought an aluminium can with you? If you've brought an aluminium can, then can you put it on a flat surface? Like, I don't know, tiled floor or a table or something. It's better if it's not all crinkly like mine is. I'm going to try and put the smoothest side of it downwards. In fact, well, yeah, I might bring you round now. What you need to do is, if you've still got a bit of plastic bag on you, can you charge it up again? And then hold it really near the metal bag, the metal can, but not quite touching the metal can, and see what happens. So I'm just going to put you down here. There we go. So you've got a good view of the can. Oh, look at that. Splendid. So I've got the can set up. It's important that the table is dry. I'm just going to charge up my bag on my head, as usual, and then hold the bag really near the can, but not quite touching it, and hopefully behold some magic. Ready? Can't see the can. There we go. Oh. Okay. What's going to happen? Oh, wow! That's the best it's been. Why is YouTube always so much better than Facebook for activities? Did you see it's moving? It's moving, but it's not touching. The plastic bag isn't touching the can. But the can rolled. Why is that happening? Why is that happening? Why is the can rolling? It's not the same. Oh, this is my best plastic bag. It's not the same as the water activity. It's not that the particles of aluminium are slightly more negative on one side and slightly more positive on the other side. And it's not even the same as the paper and the wall. It's not that the electrons are trapped whizzing around their protons, but they've been like repelled. It's not that either. What's going on? That's amazing, isn't it? How on earth do you explain that? What's happening? And finally, because I called this lesson Conductors and Insulators, what's happening is that inside metals, a lot of the electrons aren't actually bound to go around the protons at all. They are what you call free. This is what physicists call them. Metals contain free electrons. It's a little bit, well, not really anything like a pie, but it gets called a lattice structure. So inside things that conduct electricity, you have these free electrons. So the protons always stay in the same place, just kind of vibrating on the spot. But a lot of the electrons, not all of them, but many of the electrons, don't have one particular proton that they whiz around. They're just free to move around. Whereas in insulators, electrons are still bonded to their protons. So you can have this situation happening like the wall or the paper, but then they can't whiz around. So what electricity actually is charged particles flowing. So we've looked at static electricity, where charged particles have to kind of stay in the same place. The electricity that we'll look at for the rest of the module now, is electricity where charged particles are allowed to flow. So electricity flows through metals because of these free electrons. Electrons can, quite slowly actually, we'll learn about it in later lessons, but electrons can kind of slowly move right from one end of the can to the other end of the can, or through a piece of wire, because the electrons are free, whereas it couldn't move through, say, our plastic bag, because the electrons aren't free. There's no current can flow. Right, so that's what electricity is. So a conductor is something that lets electricity flow through it, and an insulator is something that does not allow electricity to flow through it. So here's a couple of examples before we test some more. Air is a great insulator because the particles of air are really far apart, right? Air particles aren't even touching each other. Their electrons are bound to them, but the electron can't really move from one particle to another. So air is a fantastic insulator. Electricity finds it difficult to flow through air. Graphite, weirdly, is a really good conductor. Graphite's sort of the only material that I can think of that isn't a metal that is a good conductor, because graphite, the stuff that you get inside pencils, does actually have free electrons in it, but mainly, apart from graphite, you're looking at metals that are good conductors. Okay, one of the things that you have to be able to do if you're doing an IGCSE physics exam is to know how to prove that a material is an insulator or a conductor. How are you going to do an experiment to prove whether something's an insulator or a conductor? Well, I'll just tell you. what you do is you get a simple electric circuit like this, and you plug different things into it. So I've got a battery here. We'll learn all about this in the next couple of weeks. But I've got some copper wire, a metal. Copper is allowing electricity, charged particles, electrons to flow through it. For circuits like this to work, energy has got to be able to flow all the way around. So we've got to get energy flowing from the battery through the bulb and then back to the battery again. But I've left a gap so we can put different materials in the way, and that'll tell us whether the electricity is flowing or not. So, do you reckon that wood is a good insulator or a good conductor? If wood is a good conductor, then when I connect this circuit up, we should see the light bulb come on because electricity will be flowing through the wood. If the wood is a good insulator, then it won't light up. What do you reckon? The bulb has not come on. Right, so question for you, please. Based on what I've just showed you, can you draw any conclusions about the wooden item? Why or why not? Based on what I've just showed you, can you draw any conclusions about the wooden item? Why or why not? This might be a trick question. I might be trying to trick you. Am I? I might be. I've just tried to complete an electric circuit with a wooden spoon. The bulb hasn't lit up. What have I proved about the wooden spoon? What have I proved about the wooden spoon? Do you see where I'm triggering you? Do you get it? Do you see? I haven't proved anything, have I? I haven't proved anything because we haven't checked that the circuit is actually working. So here's where I go, oh, kids, do you think metal's a good conductor? Do you think this metal spoon will conduct electricity? Let's see. And I attach one end of the circuit to there and one to there, and the light still doesn't come on. Oh, no, it's because I tricked you. This bulb is not screwed in properly. So for now, if I attach the metal spoon up to the... Yay, there we go, you see? So that is proof that metal, or certainly this metal spoon, is a good conductor, whereas now we've got the circuit working, we can prove that wood is not a good conductor because that's not lighting up. What about half and half? What do you reckon? What if you've got like scissors that are rubber at one end and metal at the other end? Is that going to work? No, it's not going to work, is it? Because it's not a complete circuit because we've got this big insulator in the way, so that's not going to work. Plastic, Lego brick, I feel like you get it, don't you? You get it. What about paper? It's not lighting up. Do you reckon paper is a good conductor of electricity? Got a little bit of paper here. Thinking about what we've said about paper and its atoms. What do you reckon? No, paper does definitely not contain free electrons. Electrons cannot flow within paper, so it is a good insulator. I feel like I should try one more that's a good conductor. What do you reckon if I open up these scissors? I actually have no idea. Is that going to work? Let's try. Oh, isn't that amazing? It actually works. So electrons are flowing all the way through those scissors and lighting up that bulb. Oh, so cool. Right, enough of that. So you might get asked a question like this in your IGCSE, if you're lucky. Which list contains only conductors and which list contains only insulators? And then I'll do you a little quiz to finish. Which of these lists contains only conductors? Is it A, gold, copper, paper? Are they all conductors? B, wood, paper, graphite? Are they all conductors? C, gold, graphite, aluminium? Are they all conductors? D, plastic, paper, iron? Are they all conductors? And the next question, which of these lists contains only insulators? Is it gold, plastic, paper? Plastic, paper, graphite? Gold, graphite, aluminium? Or plastic, paper, air? Water is a very good conductor. That is an excellent comment. Yes, water is a good conductor. Yeah, in fact, you just reminded me. I'll talk about that. Because people were starting to talk about the human body on Facebook yesterday and whether that was a good conductor. You got the answers? Let's have a look. Okay. Paper isn't a very good conductor. We've seen that. It doesn't have free electrons in it. Wood isn't as well because it doesn't have electrons in it. Sorry, it doesn't have free electrons. Gold, graphite, and aluminium. They are all good conductors, yes. And the good insulators, which list contains only insulators? Well, it's not going to be anything with a metal in. And that was a good one. They were testing you whether you knew that graphite is actually a good conductor. So it must be plastic and paper and air. And it is. All right, should we do a little quiz? Should we do a little quiz to see how much of that you've remembered? I have got 4 questions. Only 4 questions. And I want you to write down the letter that is next to the correct answer. And then in the end, you will have a 4-letter word. And the 4-letter word that you have will decide whether you got the questions right or not. So even if you get the questions wrong, hopefully you will have a 4-letter word. It might just be different to the correct mystery word. Let's play What's the Mystery Word? Are you ready? Which of these is charged? A wall with a balloon attached to it. If you think that is a charged object, then write S. If you think a copper wire is charged, then write T. And if you think a proton is charged, then write F. Which of these things is charged? S, a wall with a balloon attached to it. T, a copper wire. F, a proton. Which of those is charged? Write S for a wall with a balloon attached to it. T, a copper wire. Or F, a proton. Next question. The electrons in metals are, is it O, bonded, A, free, or R, loose? This wasn't actually a very good question, sorry. I haven't really phrased this very well, because in metals you've got 2 different kinds of electrons, really. You just don't need to know that. You only really need to know about one of them for your IGCSE. I should have said, unlike insulators, the electrons in metals are... That's a better way of phrasing it. Unlike insulators, the electrons in metals are, is it O, bonded, A, free, or R, loose? Next question. Which of these lists contains only insulators? Which list contains only insulators? Is it W, mercury, which is a liquid metal, wood and plastic? Is it A, graphite, air and paper? Is it I, paper, air and plastic? Or is it D, wood, gold and air? Which list contains only insulators? Mercury, wood and plastic, write a W. Graphite, air and paper, write an A. Paper, air and plastic, write an I. Wood, gold and air, write a D. And this question at the end is where everyone started to get a different word. What happens if a negatively charged plastic bag is held near a metal can? Oh, I've just remembered, oh, this is good. This is good. This is why I have to do this, because I've just realised I didn't actually really go into an explanation of why the can moved. Oh, wow. I really didn't. Okay. Well, I'll let you guess and then I'll explain it. What happens if a negatively charged plastic bag is held near a metal can? To be honest, you definitely should be able to work this out. But it was a bit mean of me not to tell you. But you've got enough information. I just didn't actually tell you. What happens if a negatively charged plastic bag is held near a metal can? Is it that the electrons in the can move away from the bag and the can becomes negatively charged? If you think that's right, write an L. If it's the electrons in the can move away from the bag and the can has a neutral charge, write an R. If it's that the protons in the can move towards the bag and the can becomes negatively charged, write a T. And if it's that the protons in the can move towards the bag and the can has a neutral charge, then write N. What happens if a negatively charged plastic bag is held near a metal can? The electrons in the can move away from the bag and the can becomes negatively charged, write L. The electrons in the can move away from the bag and the can has a neutral charge, write R. The protons in the can move towards the bag and the can becomes negatively charged, write a T. Or the protons in the can move towards the bag and the can has a neutral charge, write N. Okay, let's go through the answers and see what the mystery word was. Are you ready? Which of these is charged? Hopefully you said a proton. Most people were saying that this mystery word starts with an F. Yes, a proton has got charge. The electrons in metals, well, some of them are bonded and some of them are free, but it's the ones that are free that mean that metals are very good conductors and can conduct electricity. So it was the A that I was looking for. So we've got Fa, Which list contains only insulators? So graphite is that stuff that you get in the middle of pencils, and that is a good conductor. So the answer was I. Paper, air, and plastic. So what's the mystery word? Is it fail, fair, faint, or feign well? What happens? Let's see. Oh, that's just my face, sorry. Here's a can. Here's the negatively charged plastic bag. The can is made of atoms, right? Aluminium atoms. So aluminium atoms have the same amount of electrons as they do protons. So the can is, in real life, you know, sitting there. It's got a neutral charge. What happens when that negative plastic bag comes along is that like charges repel, don't they? Things that have the same charge want to move away from each other. So the electrons that are near the plastic bag are repelled and move over to the far side of the bag. So what you end up with is an overall negative charge on one side of the can and a positive charge on the other side of the can. But, have you actually taken any electrons off the can or added any electrons to the can? No, you haven't. So the overall charge on this can, she says, remembering how to spell neutral, is still neutral. It's still got the same amount of positive and negative charge. It's just they've moved away from each other. But unbelievably, the force of those electrons, it's so small, you can't detect them, and you can't, they're so small you can't see them with your eyes, I meant to say. They're so small, they're barely there, they barely have mass, but the force of those electrons whizzing to the other side of the can is enough to make the can move. Incredible. So the answer was the electrons in the can do move away from the bag, but the can still has a neutral charge. So the mystery word was fair. There you go. And that is the end of the lesson, except to say there's an activity that I can't do with you because, well, it's sort of quite dangerous because it involves holding a light bulb, a very thin glass light bulb. But this is a great activity to do. If you're at home, you've got an adult with you, if they think that you're sensible enough to do it, ask them first. Get your plastic bag again, charge it up the way that you would normally charge up your plastic bag. If you go to a really, really dark place, ideally just a room with no windows where it's completely pitch black, or if you get under a duvet, if you're very careful, if you hold your charged bag next to the bottom of the light bulb, the electrons on the bag will all be repelling each other, right? They'll want to move, and they will move into the light bulb. And very briefly, for a very short amount of time, you should see the bulb light up. It'll flash because there's a current flowing through it. There are electrons flowing through it, and that is what electricity is any charged particle, but usually in our houses, it's electrons. I can't show you it here because I can't see it because it's too light, and also because the camera won't pick up the tiny amount of light that it's giving off. But it is possible, and it leads us very nicely into current that we're doing next week. I'm going to go to my Facebook page now and see if anyone's left me any comments. Although you could comment on this video, of course, but I can't really see them. I don't think it shows me all the comments. I can sort of see Jacob. Oh, I can see a lot of people writing fail. I'll go over to my Facebook page, because not everyone wants to comment on YouTube, and see if anyone's left me any comments. While I'm just going over and pressing refresh, this comment about water being a good conductor. Yes, water is an extremely good conductor. That's why you shouldn't have any electrical items in the bathroom, because water can conduct electricity very well. And people were asking me, are humans good conductors? And I was saying, I don't know, people were starting to ask me things about sticking things in plug sockets. Don't ever do that. Don't ever use any kind of piece of electrical equipment a way that it wasn't designed to be used. You will learn all about electricity with me. Humans, the outside of humans aren't great conductors. So for example, if I try and complete this circuit, then the light bulb does not come on. But humans are really just bags of water, and water is a very good conductor. So there is a story, I'm pretty sure it's a true story, about, like, I can touch both ends of this battery. It's a cell, we'll learn next week, and nothing happens. If I got two tiny sharp bits of metal and spiked them into my skin and then touched the battery, I could die because the current would flow through the liquid in my body, like through my blood, and that is incredibly dangerous. Yeah, just don't mess, kids. There's no need. All right. Oh, Arthur's here. Brilliant. Hello, Arthur. Fantastic. Joined late, but we'll be watching on catch up. And here's Freya. Hello, Freya. Static electricity is fun. It is fun. It is. Oh, Bastian's here as well. Oh, brilliant. Nice, you lot. Thank you for saying hello. That's lovely. Well, I hope you enjoyed this. I will see you next week for when we will be learning about current. And obviously carrying on the Romans lessons in my All Ages Roman lesson. And doing another Lego story show. I think we decided we would do it on flesh-eating plants next week. If you want to support me, if you're enjoying these lessons and you feel like I should be paid for my job, then you totally can pay me. That would be great, actually. Obviously, all the likes on the videos and all the shares, wonderful as well. Oh, Timothy and Noah, of course it is. Timothy and Noah, hello, you two, commenting on YouTube. It's very exciting. And Jacob's here as well, who I'm assuming is just Jacob. Just Jacob, who I know. And who's that? Is that Riley? Oh no, it's Rain. Hello, I didn't see you there. Yeah, if you want to support me, then you can go to my About section and go to this website called Coffee and send me £5 a month. And that is how I can do this, is that enough people are choosing to do that, even though they don't have to, because I don't want to charge for anything that will help any child pass an exam. But I will send you some nice things to say thank you for contributing to my wages. Jacob, you're not the Jacob I know. You're a different Jacob. Oh, that's so exciting. Wait, and are you new? Or you just... I'm kind of... It's like... I just assumed it was the Jacob that comes to all of the lessons. And I feel like if this was real life, you would have just like taken a mask off and there'd be a different person underneath. I can't lie, I'm a little bit freaked out, but it's also very cool. I was the Sarah who did the Star Wars joke last week. Oh, okay, right, hello. Yeah, if you sign up to support me, I will send you nice things. I will send you some rainbow glasses that make you... I can say diffraction glasses because you're doing IGCSE physics. They are diffraction glasses, which we will learn about when we do diffraction. And I'll send you a description of how they work. And if you sign up with £5 a month to support me, chip into my wages, cancel anytime, I will send you a copy of the mould magazine that I wrote. I write a Theatre of Science magazine. It's incredibly sporadic. I just get it finished when it's finished. The next one is coming out quite soon. So this one's on mould. It's got a cartoon. It's got a choose your own adventure. I send you a free compostable plastic bag so you can grow some mould and then maybe identify it using the mould spotting guides. And if you sign up with £6 a month, then you will receive... Oh, hello, Wolfie! You will receive this magazine, which is on sleep. This is another past issue. It's also got a beautiful comic that my husband illustrated. It's got a little jigsaw about sleep. It's got an origami koala that you can make. It's got a choose your own adventure, and it comes with a little bag of organic lavender and some fabric so that you can sew a sleep squish, which will hopefully help you sleep. Right. Advert ends. Thank you so much. Thank you for all the likes. Oh, it's Ollie. Sorry, Ollie. Hello. Thank you for all the likes. Thank you for liking and subscribing. Thank you for the sharing. And thank you also for the actual cash money allowing me to feed my family, etc. All very much appreciated. Hello, King. Hello. In capital letters to you. This is very cool. I'm enjoying these comments. Right. I'm enjoying the comments, but I'm going to go and work on some magazine, actually, and pack up some supporter packs. So thank you very much once again if you are supporting me. And I will see you next week, she says, just quickly refreshing. No more comments. Okay, I'm going to go now. Bye.